Hi everyone, let's get started on this second part of our metabolism lecture. And so our goals here are to investigate the concept of molecules that carry energy from one chemical change to another. So these activated carriers, and you've seen some of these before, and we're now going to take a look at the structure-function relationship of these activated carriers. So a recurring theme in metabolism is the use of these, what we're calling activated carriers. ATP is an example you've seen before. It's an activated carrier of phosphate groups. And we know that because it carries the phosphate group right from one thing to another. That phosphate group's hydrolyzed off in this exergonic process that gives off the energy and allows that group to be transferred to something else. So a couple or three pieces we want to look at. First of all, these carriers are kinetically stable. And let's talk about that. So in the example of ATP, we know that it is thermodynamically unstable because we know it has a large negative change in free energy, right? Delta G is much less than 0. So it is thermodynamically unstable. So we would expect, if there was no kinetic problem, that this would just go to products. Those products are much more stable, much lower energy. But because it's thermodynamically stable, the reaction is really, 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 really slow. So remember when we talked about kinetics, we're talking about speeds of reaction. And we talked about having this activation energy, this hill that we have to get over. So even though these things are thermodynamically unstable, we'd expect them to go to products. The reality is that activation energy is so high that these carriers hold on, in this case with ATP, to that phosphate until there is some enzyme to help reduce this activation energy, and hence it can now let go of that phosphate. So the second piece we want to look at is that the metabolism of activated groups is accomplished with a small number of carriers. Okay, we're going to see the same carriers used over and over. So we can talk about phosphate transfer, electron transfer, 2-carbon group transfer, 1-carbon group transfer. These are part of lots of oxidative reduction reactions, but just a small number of molecules are the carriers of these electrons and these phosphates. And then another key point is that what we're going to call this modular design and economy of metabolism. The fact that there are the same carriers across multiple species, different cells in the organism, it supports this idea of kind of the evolution of biochemistry, that these same things we see over and over again. Let's look at some examples of carriers. ATP is an activated carrier of phosphate groups. Okay, so in this particular reaction, we see that the phosphate will stay on that ATP until there's an appropriate enzyme present. Okay, kinase move phosphates from the ATP. And in this case, we see that phosphate right here, this phosphate is added to that 6th carbon. And this is a molecule, this glucose 6-phosphate, that we're going to see again in glycolysis. And this is important because this activates the glucose. It tags the glucose so it can enter metabolic pathways. And we're going to look at that pathway, one of those in glycolysis. Let's look at the second reaction. So here we have this NAD plus Okay, we're going to look at the structure of that in a minute. And it picks up electrons. So over here now, it's gained electrons, 2 actually, because notice it no longer has a positive charge and it has that hydrogen. And so these electrons are activated in part of this NADH. And so NAD plus is a carrier of electrons. In this case, the energy to add those electrons to the NAD plus came from this oxidation process, right? We see that we're oxidizing our fuel. It gives off some energy. That allows us to reduce the NAD plus to NADH. You will often recognize redox reactions by the use of these carriers. So oftentimes if you see ATP, you see NAD plus, you can expect a redox reaction. All right, let's look at some of the structures. I said we were going to focus on the structure-function relationship. ATP, ADP, AMP. We've looked at this molecule before, but it has the adenine piece shown in blue, the ribose sugar shown in black, and then the phosphate groups. And they differ on the number of phosphates. So we have triphosphate, diphosphate, monophosphate. And we've talked about these before as we talked about the energy that's released, but now we're going to start thinking about them as this carrier of these phosphate groups. Those two things are entwined, but just a new focus here. All right, let's look at the NADP, and I cut that off, didn't I? NADP or NADP plus. So we've got 2 possibilities. Whoops. So nicotinamide adenine dinucleotide, and it can either have a phosphate or not have a phosphate. So when we look at this, okay, we are really looking at, so notice the terminology dinucleotide. I'm going to draw a line through this thing. So if you look at kind of this bottom half right here, this looks a lot like that AMP from above, okay, the adenosine monophosphate. So we have the adenine, we've got our ribose, we've got the phosphate group, but now it is bound to this nicotinamide, this second nucleotide up here. And this particular one is NADP. It's got that phosphate group, but this would be a hydroxyl group if it was just NAD+. So NAD+, NADP+ is considered a coenzyme or a co-substrate. We've used that term, I believe, before. So when we have an enzyme acting on a compound, sometimes there needs to be another substrate there. And so this would be a co-substrate. So it'll be together in the active site with something that's being oxidized or reduced. So if something's being oxidized or reduced, there has to be something else there to either give or take those electrons. This is a huge molecule, but if we look at it, we have this kind of reactive site up here. That piece will be the piece that goes into the active site. And again, it is, well, not again, but I mentioned earlier that the phosphate can tag something. So if we look at this phosphate here, it turns out that NAD plus often carries electrons for oxidizing fuels. So it carries it down to the electron transport chain that we'll look at later. NADP plus tends to carry electrons to synthesize things. So this is for a biosynthetic route. Okay, this would be oxidizing fuels route. So one for energy, one for synthesis. Okay, and the body knows which one to use from this phosphate tag. Let's look at the process, and so we're going to look at just this part here. Okay, and I've redrawn just that active part. It's in a little different geometry, but if you match it up, it matches up. The rest of the molecule is this R group. And let's look at what happens. So if we want to go from NAD plus to NADH, we need to gain that electron and that hydrogen. And so what we have is we have a hydride ion. So it's a hydrogen with 2 electrons. So you can think about one of these with these 2 electrons. And that's going to come in right here. So when that happens now, that carbon can't have those 5 bonds. So these electrons are going to move here. These electrons are going to move here. We get rid of that positive charge. And we end up with this molecule on the right, along with 1 H plus left over. Often the H plus isn't shown. It's in solution amongst all the other hydronium and hydroxides. So we often don't show that. NADP would be the exact same process. There are a couple other activated carriers. Let's look at those. So flavin adenine dinucleotide. They're all a mouthful, right? So this is a derivative of riboflavin, this kind of blue part up here. And when this picks up electrons, let's actually take a look at it. This is a carrier of electrons. And now we're looking at just this area, this top piece with the reactive site down here. And so we see that it goes from FAD to FADH2. Again, it's going to carry a couple electrons. And again, we're going to think about a hydride ion attacking this top nitrogen. It brings its own electrons, so it can form a bond. We see that over here. Okay. And when that happens, again, these electrons will move here, these electrons will move here, and now that nitrogen has a pair of electrons it can use to bond to that second hydrogen. Okay, and so we see the changes over here as we've added there and there. Okay, this is reversible. It can pick up electrons, it can drop off electrons. All right, another one. So this coenzyme A is an active carrier. Now this is different, right? Not of electrons, not of phosphate, but of acyl groups or acetyl groups. So let's just remember what those are. So the acyl groups are that carbonyl with some R group on it. And when we talk about acetyl groups, that R group is specifically methane. So this molecule we see over at the left, the green, here's our ADP. Okay, it's phosphorylated, but basic idea of it. And then we've got this middle piece and then the end. And what I really want to focus on here is this thiol group. Okay, that can react. Picture something like acetate coming in. So I've got we can get a dehydration going on here where the hydroxide and the sulfur would leave as water. And then if I look at what would be left, I now have this structure at the end, and then it goes on to the rest of the molecule. Okay. This is a important molecule because this thiol ester, right? It's an ester, got the carbonyl piece, and then you've got this thing bonded, but now instead of an oxygen, it's that sulfur. So it's thioester. And this is a really high energy bond. Okay, so this bond right here is high energy. We can break that bond, get a lot of energy to move reactions forward. when you look back at these FADs, coenzyme A, ATP, you're going to see a lot of similarities. There was another one, NAD plus. They all have some sort of ADP or ADP-like piece to it. 3 or 4 of them have a vitamin as a part of it, and we're going to kind of come back and look at that. And so we're going to be looking at these now as we start looking at glycolysis and looking at this mechanism by which we get energy. So this is a chart just of some activated carriers. And you can see here's the thing they carry. So carbon dioxide, aldehydes, acyl groups, electrons. Here's the names of them. You don't need to memorize these. And here's the vitamin precursors. You also don't need to memorize those, but look at it. B3, B2, B2, B5, so on and so forth. So many of these activated carriers are derived from vitamins. These ones in green, the B vitamins, are the ones that are typically included. These other vitamins play a variety of roles, but generally do not serve as coenzymes. And as you look at them, you can see that these things tend to be they have less hydrophilic pieces, right? When you look up here, lots of hydroxides, lots of charged area, and those tend to be the things that get pieced in these coenzymes. So this is more just for interest. It talks a little bit about the different vitamins, okay, and the type of reaction that vitamin, so it's incorporated into this coenzyme, type of reaction, and consequences of deficiency. Most people get enough vitamins. If you eat a balanced daily diet, generally most people get enough vitamins from their diet, with the exception of folic acid for women of childbearing age. But that does depend on your balanced diet. Non-coenzyme vitamins, again, same thing. Just for your information, for interest, vitamins, roles, and deficiencies. All right, next we get to talk about much more specific reactions as we start our lecture series on glycolysis.